Good morning, everyone. Good morning, everybody. Good morning, everybody. Good morning, everyone. Welcome to CHM 121 today. Our class is meant to start by 9 o'clock, isn't it?
Yeah.
Hello, ladies and gentlemen. Our class is meant to start by
yes, ma'am.
Yes, ma'am.
But how come so few people are around? Is it that they don't know?
Yeah, probably in another class.
Anyway, I'll teach. I think we can record it. This is the official time on the timetable, so it ought not to clash with any other time. If it does, it means those people schedule it. This is our official time. Okay, I'll just go ahead teaching. But you need to tweet or call your friends, because this this second part of the lecture is a build up on is a build up, and you'll be needing all this information for subsequent lectures. So if you miss this, you may be able to grab, or you may not be able to grab what other lecturers will be teaching. Okay, I'm Dr. Fatosi Oluwatoyi, and I'll be taking you through everything you need to know about solutions and associated things related to solutions. And the goal of today's lecture is to define solute solvents, different types of solutions, and how to understand the charts. How to understand the charts. So we'll start, before we go into solution, I'll start with mixture. So what is mixture? So mixture is when you combine any two things together, two or more things together. And if they can be physically separated, we say it's a mixture. So for example, if you put stones, gravels, and beans, we can separate it. So you have a cup of beans, a cup of stones, a cup of gravel, and you mix them together. Then that is a mixture. So you can physically separate it. But when you cannot physically separate it, it's called a chemical. It's no more a mixture. So for compounds, if they cannot be physically separated, it's not a mixture. A mixture is something that you can physically separate. But when you have two or more things reacting together, they form a new compound. We say it's compound. Because you cannot, for example, if you bring sodium and chloride together and they react together to form sodium chloride, and you have salt, can you separate the sodium from chlorine physically by just pulling it apart in our table salt? No. So that one is a compound. But mixtures are when you bring two or more things together and you know you can physically separate them. So a very good example of what I've just told you. Beans, raw beans, and gravel, big stones. Then we have what we call heterogeneous mixture and homogeneous mixture. The term so heterogeneous mixture, they look very different, even though they are mixed together. But homogeneous mixture, they look uniform. So solution is a type of homogeneous mixture. Solution is a homogeneous mixture, and we'll be delving into solution. So we're starting from mixture to solution. Mixture, when you bring any two things together, a case in example is stone and gravel. Now, when you can physically pick your beans from your gravel, so it can be separated physically. Now we have two main types of mixtures. I'll be sharing the slides with you. I'll be giving you the slides, the material. So we have two types of mixture, heterogeneous mixture and homogeneous mixture. Heterogeneous mixtures, they look very different, like beans and stone. But homogeneous, they blend together, they look uniform. So solutions are a type of homogeneous mixture because in solution, two things are brought together that can be separated, but they mix well. They look like one. So example of a solution is our tea. Tea. They are mixing well. We know that they are definitely two different things. If you leave this tea for some time, for a long time, you will see the tea floating and the milk settling, but it will be a really long time. You see, your rice in water is a mixture. I don't want to answer. Rice in water, is it a mixture, a solution? Is it a heterogeneous mixture or a homogeneous mixture?
Homogeneous.
Hello? Is a homogeneous mixture, so we can call it a solution. So generally, we actually use the word mixture for heterogeneous mixture most times. So when we are referring to solution most time, we know that they are homogeneous mixtures. Look at this, oil in water. Is it a homogeneous mixture or heterogeneous mixture? It's heterogeneous because they don't really blend, except if immediately you've stirred it, but most times they'll separate. Look at sand in water. Is it a solution or a mixture? Is it a heterogeneous mixture or a solution? Sand in water. Sand in water is a heterogeneous solution. They don't really blend like that. Yes. So heterogeneous mixture. So it's more of, we use the word more of mixture for them. But when they begin to blend, we use the word solution for them. Even though we know that mixture is divided into two. We have heterogeneous mixture and homogeneous mixture. So there are different kind of solutions. Solutions can be gaseous, can be liquid, or can be solid. Solution can be liquid, gaseous, or solid. And in a solution, you always have the solute and the solvent. In a solution, you will always have the solute and the solvent. In that mixture, there are two parts. Now, the one that is more is the solvent. The one that is less is the solution, is the solute. So in tea, what do you think is the solute? What do you think is the solvent? Tea made up of water and milk. Which one do you think, in an average, not excessively rich person, in an average person's tea, which one do you think tea made up of just water and cream? Which one do you think will be
The
the
solute.
solvent?
Water is the
Which one would you think will be the
Water.
solute?
The water is
milk
the
Yes,
will be
can
solvent.
somebody talk to me?
milk will be the
Water
The
will be
water
the
is the
solute.
solvent,
solvent.
because why the milk will be,
Yes.
because water is usually more than the milk. So yes, so that's it. So the one that is more is the solvent, the one that is less in your solution is the solute. So a solution is a homogeneous mixture of solvent and solutes. The solute usually dissolves or blends well in the solvent. In solution, the solvents are physically combined because you can separate them one way or the other. If they are chemically combined, then it's a reaction that took place. But when they are just physically combined, such that one way or the other, they can be separated, then we say it's a solution. But once reaction is involved, it's no more a solution. It's now a new compound that you formed. There are other solvents. We know that water, many of us know water as solvent. But in chemistry, there are other solvents. Anything, when you mix two things together, and so water can become a solute in certain instances. So let's say you put too much milk and has smaller quantity of water. Water is no more the solvent. Water is now the solute. Why that milk is the solvent. So, for example, let's look at this. You have our soda, our drinks that we drink, our fizzy drinks. That's our Coca-Cola, Fanta, our fizzy drink. Water is the solvent because in all of them, water is more. Our sugar is less. CO2 is dissolved. So this solution is made up of gas and liquid. It's made up of solid and liquid. We also have other types of solution. Air. In air, we have hydrogen, we have oxygen, we have other trace gases. But we know that air is made up of 78% nitrogen. And since nitrogen is more than every other gaseous component, we know that nitrogen is the solvent, while other gaseous components are the solutes. So in air, other gases are the solutes. In our gold that we wear, those of you that wear gold, most people do not wear 100% gold. That's why we have different carats of gold. The carat tells you the amount of gold that is in that mixture. So most of our gold that we say we have gold are actually mixtures. It's just that maybe gold is more than other metals, but they're actually mixtures. So when you say you have 24 karat gold, it means there's more gold than other impurities. When you have 8 karat gold, there's lesser gold. The impurity is higher, but the gold is still more. So as the carat of gold is increasing, the amount of gold is more, and the amount of other metals are less. So gold is also a mixture. And so there are other examples. Can anybody give me other solutions that we use that you can think about? How about our perfumes? Our perfumes. Usually the solvent, alcohol, or any other organic solvent, and your essential oil are usually small, dissolved in it. Can you give me other examples of solutions that we use every day? Solutions. Like your ogi. When you make your ogi, you dissolve the ogi inside it. It's initially blended together, and then when it settles, you see them separating out. That's the kind of solution. Yes, I've said it. Now let's look at this question. I need people to answer. So everybody on mute, so you answer. One person would. Once one person is speaking, others can keep quiet. A perfume consists of two gaseous fragrances, A and B. So which one is the solvent? Hello?
Fragrance
B.
B is the solvent.
B.
B is the solvent. Why? What is the solute here? A
Fragrance A.
is the solute. Now let's look at question 2. A milk vendor has 2 cans of milk. The first can contains 25 water. The rest is milk. The second contains 60% water and 40% milk. Identify the solvent and the solute in can A, in can 1 and can 2. So in can 1, what is the solvent? In the first can, what is the solvent?
Milk.
Eh?
The milk.
Yes.
Milk.
In can 2, what's the solvent?
Water.
Water. And in can 1, what's the solute? Milk.
Water.
In the can 1, water is the solute. In can 2, milk is the solute. So so milk and water is not always that. What's that? There's an echo. So the milk and water. So it's not every situation that the milk is the solute, and it's not every situation that the water is solute. You have to look at the case specifically. Okay. So that leads me up to a new concept: saturation, unsaturation, and supersaturation. I want you to look at, imagine, if it was a physical class, I would have brought some things to demonstrate, but there's no point. Just close by and imagine that we had bought 50 naira sugar or 100. There's no 50 naira sugar again. We bought 100 naira sugar, and we took a big cup. I want you to use your imagination. And we took a giant cup, and we put this 100 naira sugar, and we put a teaspoon of water. What do you think will happen to that water and the sugar? A teaspoon of water. Will it dissolve the sugar totally? Hello, please, this is an interactive class. Can somebody talk to me? Will it dissolve the water?
No.
It won't dissolve the water totally. A teaspoon of water in a big jar with 100 naira sugar. Some of you are bought, you've never bought 100 naira sugar, but those of you that bought 100 naira sugar, those sugar that they tie, those granulated sugar that they tie. But even if you've not bought sugar in that form, at least cubes of sugar, just imagine you took, at least everybody would have seen cube of sugar. Just imagine you took 5 cubes of sugar and you put in a big cup and you took just 1 teaspoon of water. Do you think it will dissolve those cubes of sugar? No. But it will, at least the sugar will be a bit melted, but will not be totally dissolved. Now, as you add another teaspoon of sugar, more of the sugar will dissolve in the water. And then as you add more will dissolve. As you continue adding teaspoons of sugar, a point comes where there'll be no granules of sugar. All the sugar will be completely dissolved. So now, let's look at it this way. You were adding water. When you added water, initially, the sugar did not even look like it was dissolving at all. Then you added more, you notice that the sugar is dissolving, but there's still water on top. Even if you stir, the sugar will still remain. In that scenario, we say we have a supersaturated solution. A supersaturated solution. Now, you continue adding, you add another teaspoon of sugar. The thing you still seeing granules. Now, you add it, maybe you add the water drop-wise. A particular drop, you add a particular drop where you find out that the last granule of sugar just dissolve. Say we have a saturated solution. A saturated solution where just 1 drop extra of water dissolve the last crystal we say we have a saturated solution. And that saturated solution, if you leave it or if you leave it near heat and it dries and it starts drying, your granule of sugar will start coming out because you have a saturated solution. Now, when you add more water such that it is now dilute, it's no more thick, the solution is no more thick, it's no more, you've added enough water, we say we have dilute solution. So when you have a saturated solution, if you leave it and the water evaporates, you see crystals coming out slowly. We say you have a saturated solution. Saturated solution can, if anything happens, if it becomes, if the water reduces, you begin to see your crystals coming out. So let's begin to define our terms. I just use that to explain what we're trying to say. Look at all this here. We have supersaturated solution. Look at figure 3.1 to 3.3 are all supersaturated solutions because you see your granules here, there. And here you see that there's more solid and solute in figure 3.1. In figure 3.2, the more crystals are coming out, but it's slower. And in figure 3.3, more crystals. Sorry, they are crystals. They are less crystals. When you dissolve in a solvent, when you dissolve it, you have a particular concentration. So you can imagine dissolving a teaspoon in a big bowl of water, in a big cup of water. Yes, the solutes are there, but it's diluted. And then when it's diluted, the solutes hit each other as they move and they dissolve. They hit each other, they dissolve. They hit each other, they dissolve. Now, if there's more solvents in that cup of water than the solute, the chances that they will ever meet each other and collide is very slim because they are diluted, they are far apart. The distance of this solute to each other, solid solutes to each other is slim. Now, as the solute particle increases, so just imagine that cup of water, you keep adding more solutes, more sugar, you keep adding. As they dissolve, they will hit each other and be attached. These solutes will hit each other to dissolve. And as they hit each other, instead of dissolving, they will attach to each other. This process of colliding with each other in solution and attaching to the other leads to what we call crystallization. And so you begin to see solute deposited at the bottom of the cup. The point comes when the rate of opposing process becomes equal, there is no further net increase in the amount of solutes in the solution, and a dynamic equilibrium is obtained. So we are saying that a point comes when this heating, colliding, when maybe you are adding the solutes, they are colliding with each other, they are dissolving, you are adding, a point comes that they will attach to each other, equilibrium is met, they attach to each other, they deposit, they attach to each other, they deposit. We say we have what we call supersaturation because it's saturated. When the solute can no longer dissolve anyone, we say it's saturated. A point where the solute can no longer dissolve, the solvent can no longer dissolve the solute. We say we have a saturated solution. And at that point, when they collide, they begin to deposit. We say we now have a supersaturated solution. I repeat myself, when you have a solvent and you have solute, when you drop your solute, they move in the solvent, colliding with each other, dissolving. Now, a point comes, you continue adding your solute to that solvent. A point comes, they dissolve, but they clash with each other in the solution, in the solvent, sorry. They clash with each other, and they attach to each other. Then a point comes that equilibrium is attained, whereby they hit each other, but they are not yet deposited, but the solvent is able to carry it, is able to allow them still some distance and dissolve, but it's heavy. Now that we say we have saturated solution. Now a point comes where when they hit each other, they attach to each other and deposit at the bottom of the container in which they are. We say when they begin to deposit, we say crystals are coming out. That's crystallization. We say we have a supersaturated solution. So it's only in supersaturated solution you have crystals coming out. In saturated solution, it's just at equilibrium. It's just able to accommodate the solutes there. But after it's able to accommodate, a point comes that solvent is not able to accommodate, it begins to deposit. We have crystallization, and this occurs in supersaturated solution. Now, if you want to have crystals, sometimes we do what we call seeding. So you are adding to make sure that you're adding a few crystals to the solution to make sure that you exceed the saturated states so that crystallization comes. Those of you that will go on to do chemistry in year 2, you will carry out this experiment of crystallization. Now let's look at this. Certain things affect the solubility. Certain things affect solubility. That's the process of that solute dissolving solvent. Certain thing affects the ability. At 40 degrees Celsius, the solubility of KBr is 80 grams in 100 grams of water. Indicate the following solution is following. Now let's look at this in A. At this same temperature, now you now put 60 grams of KBr in 100 grams of water at 40 degrees Celsius. Do you think that we have attained? What do you think? Which kind of solution do you think we have here? We'll have it's a solution that is not yet saturated. So we'll have 2. A is equal to 2. Look at this question again. Remember we said that we have a point where we have saturated, where the solution is saturated. So the solubility of KBr tells you the point that above that, you might not be able to dissolve any more KBr in water. That's what solubility tells you. That above that condition, if you put more, nothing will dissolve, will be leading to supersaturated solution. Below that below that amount, there will be the solution of that solution. Now look at this question. Please, somebody who is willing to answer can answer. Now look at this now. 60 grams of KBr dissolved in 100 grams of water. What do you think is it? The chat box, can you answer me? What do you think it is? Is it saturated or supersaturated? Drop it. So A is what? Unsaturated. A is 2, unsaturated. How about B? B is what? 200 grams of water.
Supersaturated.
Super, yes, because it's 80. It has exceeded 1800. C is what?
Supersaturated.
You can drop your, okay, you can say C will be what?
Supersaturated.
C?
Supersaturated.
C is not supersaturated. C, look at C is 25 grams.
C is unsaturated.
So it will be 50 grams in 100 grams. 50 grams in 100
C is
grams.
unsaturated.
B, look at it. Look at this. Listen to me. B cannot be. Look at this. Sorry, I'm talking of C. Sorry, I've moved to C, but I'm mentioning B. C. Look at 25 grams in 50 grams. Look at it. 25 grams in 50 grams will be unsaturated. Sorry, I was referring to C. I'm still mentioning B.
Unsaturated.
So C is unsaturated. B is supersaturated. A is unsaturated. Do you agree with me?
Yes, ma'am.
Yes. So we move to the next slide. There's an echo. Somebody is listening to YouTube and listening to Zoom together. We're not doing the demonstration. I told you to imagine that. So we have, you know, in my introduction, when I was telling you about solutions, I told you that air is a solution. I told you that Coca-Cola and all our fizzy drinks that we drink are solutions. So we want to look into somebody managing my slide. Why? So we want to look into the different forms of solutions that we can have. Solutions do not always have to be in the same physical state. As in, the components of solutions do not always have to be in the same physical state. So we can have solvents in which the solutes and the solvents are in different physical states. As long as they combine well, homogeneously, is still a solution. Example, look at seawater. Seawater is rich in different salts. You have different solutes, you have different ions in seawater. But when you see seawater, it's homogeneous. So seawater is a solution, but it's made up of solids and liquid, and even gas. Do you know that oxygen dissolves in seawater? That is why our fishes can survive in water. So it's a homogeneous solution, even though it has things, it's made up of, its components are in different states. In seawater, you have gas, you have solutes, you have solids, and you have liquid components of seawater. So we want to look at different forms of solution. We have gas in gas. I've already told you. Air. Air, the solvent is nitrogen. And then the solutes are oxygen, argon, and many other trace gases. We have CO2, etc. We have gas in liquid. Examples are carbonated drinks. Coca-Cola, Fanta, Pepsi, Lacasera, all of them. Gases, when you look at it, you don't see the gas in it, except if you shake it, then you see it. So the gas is well blended with the water. You have gas in solid. Example, hydrogen gas in palladium metal is usually trapped and mixed well so that you don't see. We have liquid in liquid. Example is gasoline. In that our gas, in our fuel, many things are mixed together to give us our fuel. We have liquid in solid. Liquid in solid. Example is our mercury in silver. You know, mercury is liquid and silver is solid, but it's mixed to make our filling dental amalgam. Although they've tried to stop mercury from being used now, there are newer types. But mercury in silver is this liquid in solid solution. We have solids in liquid, seawater, sodium chloride, and other things that dissolve in it. We have solid in solid. I've told you of gold, our gold, different carats of gold, our metal alloys, different types of metal alloys. They are all solutions. Does anybody have questions here for me? Does anybody have questions? Does anybody have questions for me?
Yes, Mama. Can you please explain that super saturated again?
So when you say we have mixed a solution, when we have a solution, we have a solute and a solvent. Solute is less than the solvent. The lesser one is the solute, the one that is more is the solvent. Now, so I started with imagine you have just close your eyes and imagine you have a cup of water. You have a cup of water, a small cup of water. And then you bought maybe 300 naira sugar. You started pouring it small. So you pour the first 100 naira sugar or the first cube of sugar and you are stirring. When you pour it and you are stirring, it's dissolving, right? It's dissolving. It's dissolving. It's dissolving. It's dissolving. And then a point comes. It gets thicker. It starts thickening. it starts thickening, but you don't see anything deposited at the bottom of your teacup. You keep adding, you bought plenty sugar, you keep adding, keep stirring. So at the point where it's thickening, but nothing is dropping, we are at the saturated point. But a point comes, you just add one more crystal, and you see that it begins to deposit. It begins to deposit at the bottom. No matter how hard you stir and wait, there will be deposits. Then it means you've got to the supersaturated point. So there are three phases in that mixing. When it was diluted, it was unsaturated. You were mixing it and it's just flowing well, it's dissolving. Every drop you add, it dissolves. A point comes where it keeps dissolving, but you notice it's thickening. It's thickening, but it's dissolving, but it's still thickening. A point comes whereby it's thick, a point, and then you drop one more crystal, and then it deposits, it refuses to dissolve. The point just before the deposition of that crystal at the bottom is the saturated point. The point just before the deposition of that one crystal is the saturated point. So if there's a way of removing that one crystal, it means that is a saturated solution. So when you add any more crystal, it won't dissolve. It is supersaturated. Any more crystal of sugar, it will be settling, it won't dissolve. It will just keep piling and piling and piling. So we have a supersaturated solution. So now the science behind it is that when you put the first few granules or cube of sugar, they move around in the water. They move around. But the distance between the granules are far. So even when they move out, there's enough space to move around. So there's no problem. They're not affecting each other. Now, when you get to, as you keep adding, a point comes that they become saturated. At that point, they are hitting each other more closely. There's no space. They are hitting each other too much. The solutes are colliding, though dissolving, but there's no space. It's colliding. And so it's colliding. And when you add one more at the supersaturated condition, when you get to the supersaturated point, they are colliding, and they collide and attach to each other and fall down because there's no space to move around. It collides with each other and deposits because there's no space to move around. At that point, you say you have a supersaturated solution. In saturated solution, they are colliding with each other. They collide with each other. They gum to each other, but they leave themselves. They collide, no space. But a supersaturated solution, they collide with each other and deposit. Do you now understand what I'm trying to explain? Yes. And I gave you some examples of solutions. Remember, tea in water is a solution because if you leave that tea for a very, 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 very long time, there will be a separation. There are different phases. There are different things. Rice in water is not a solution. It's not homogeneous. So we'll say it's a mixture. It's a heterogeneous mixture. Solutions are homogeneous mixture. Why heterogeneous mixtures are also mixtures, but they are not in the same phase. They don't blend with each other. They don't blend. In solution, the solute and the solvent mix together and blend well. It's just that the blending is physical. It can be separated using one or two of the separation techniques. Sand in water is a heterogeneous mixture, is a mixture. Oil in water, if you've blended it well, may a homogeneous or heterogeneous mixture, depends at the point. And I gave you some examples of water, of fragrance mixed together in that ratio and all that. So I guess now you can explain the concept of, so supersaturation leads to crystallization, where the crystal gum to each other and deposit at the bottom of the container. So in supersaturation, you have crystal formation, and you can improve on crystal formation by seeding. So by consciously adding seeds to a saturated solution, you help the crystals to come out fast. So when you are doing crystallization in the lab, the process of seeding helps the crystals to come out. Another thing that helps crystal formation fast is cooling. So if you cool the solution, the saturated solution, crystals will come out. Because you know that maybe, I think it's part of the thing. Okay, it's part of the things we are looking at now, so no need to go. Let's go into our lesson for today. So I introduced solubility subtly, where I told you that 60 gram per 100 gram of water is the solubility of KBr. So if you have 200 gram in 100 gram of water, it's supersaturated. But if you have 20 gram of KBr in 100 gram of water, is unsaturated. So solubility is a measure of concentration. Solubility is a measure of concentration. As you go higher, you see that sometimes we use solubility in exchange for solution for concentration. But solubility is a measure of concentration. So solubility refers to the maximum amount of solute that can dissolve in a particular amount of solvent under specific conditions. So in solubility, you must state the conditions. That's where it differs from concentration. In solubility, you must state the conditions. So, for example, solubility, you say 85 gram of KNO3 dissolves in 100 gram of water at 55 degrees Celsius. So higher than that, it might be able to dissolve more. Lower than that, this amount of KNO3 may even reduce. Now, only 36 gram of NaCl would dissolve in 100 gram of water at 55 degrees Celsius. You see that their solubility is different. So KNO3 is more soluble than NaCl. That leads me to what we call solubility curve. Solubility curves are plots that helps us predict or understand the relationship between solubility and temperature. So now let's look at this curve. Ki, look at Ki. Ki there at 0 degrees Celsius, only 130 gram would dissolve. As you increase the temperature to 30, to 20, more, about almost 150, or let's say 145 gram would dissolve in water. Now let's look at sodium nitrate. Sodium nitrate at 0 degrees Celsius, 70 gram would dissolve. As you increase the temperature, much more would dissolve. Much more dissolves. The temperature, it dissolves more. So which compound has a solubility of 61 gram per 100 gram of water at 70 degrees Celsius? Yes, at 70 degrees Celsius, 61. You use the graph to look at it. At 70 degrees Celsius. What? NH, yes. So that's what you can. So the solubility curve has told you what temperature, as in the conditions for dissolving a particular amount of solute. Which compound has a solubility of 41 gram at 100 degrees, at 41 gram in 100 gram of water at 50 degrees Celsius? 41 at 50 degrees.
HCl.
Yes,
HCl.
correct. HCl, correct. HCl is the best. So that's what solubility curve tells us. So we can go on and on and on. HCl. 41 degree, yeah. KCl, yes. So that's the answer. What? So certain factors affect the solubility of solvents, of solutes. Number one, I need you to take note of this in your notes. Solute-solvent interaction, temperature and pressure. You know your exam is OBJ. These are the kind of questions we can ask. I can give you a solubility curve and tell you to predict which salt, the solubility of specific salt at specific temperature. I can tell you to define supersaturation or to explain supersaturation. I can explain supersaturation and tell you to tell me, is this scenario a saturated solution, unsaturated, just like we gave you, or a supersaturated solution? I can tell you, so I'm giving you the kind of questions I can ask in my past now. So that, because after this lecture, after two more lecturers coming in, you will have tests. 2 more lecturers are coming in after me, then you have tests. So I can tell you what are the factors affecting solubility. You will tell me solvent-solvent interaction, temperature effects, and pressure effects. So under, I told you solute-solvent interaction. Under solute-solvent interaction, we have molecular mass and polarity. Molecular mass and polarity. You know that molecular mass is also called molecular weight. So under solvent-solute interaction, there are 3 things first that affect the solubility of our substance. One, what is the first one? What's the first one? Solute-solvent interaction. The second one, solute-solvent interaction. What's the second one?
Temperature effect.
And the third one, pressure effect. So under solute-solvent interaction, what are the 2 things we are considering? Under solute-solvent interaction, what are the 2 things we are considering?
Molecular mass and
Molecular mass or molecular weight, and what?
polarity.
And what?
Polarity.
And what? Polarity. Please answer me so you remember. When you see and say, you remember. So molecular mass and polarity. Molecular mass and polarity.
Polarity.
So I want to explain molecular mass. Now let's look at it. Now, under molecular weight, increase in surface area of the solid increase the solubility. Now, if you add a cube of sugar in a bowl and you add to one bowl and you add crushed sugar, that's the granulated sugar, to the other bowl, which one do you think will dissolve faster? The crushed sugar will dissolve faster because it has a wider surface area than the cube sugar. Cube sugar will first take some water to dissolve, to become granulated before it starts interacting. But the granulated sugar immediately begins to interact. So now, under molecular weight, we look at the size. Now, nitrogen has a molecular weight of 28.03 this. Nitrogen is not polar. So we are looking at this table now. Look at nitrogen, CO, oxygen, argon, and this K are krypton. Now, nitrogen is the most soluble, followed by CO, followed by oxygen, followed by argon, followed by the Kr. Now, why is nitrogen more soluble? The molecular weight of nitrogen is less. Nitrogen is not polar. The nitrogen and nitrogen, they have the same polarity in nitrogen gas. So there's no polarity there. Now, looking at CO, it's polarity now because carbon and oxygen have different polarity. The molecular weight. Okay, you know what? Let me explain it first and foremost. Let's look at all their molecular weights. Nitrogen has the smallest molecular weight, followed by CO, or they're about the same thing, followed by oxygen, and followed by argon, and followed by krypton. Now, so krypton, because they have the higher molecular weight, is least soluble. Argon is less soluble than is more soluble than krypton because its molecular weight is less. Oxygen is more soluble than argon because its molecular weight is less. We are looking at oxygen. Oxygen is 16 times 2. So that's why it's almost 32, you can see. Now, this nitrogen and CO, carbon 2 oxide, they have about the same molecular weight. But you see that even though they have about the same molecular weight, nitrogen is more soluble than CO because CO is non-polar. Polarity will reduce the solubility compared to nitrogen. Nitrogen molecule has 2 nitrogen gas. So 2 nitrogen atoms, sorry. And so they are the same polarity. So there's no charge anywhere. They are the same. But CO, the oxygen will pull the electron to one side. And so it will begin to attract hydrogen. Hydrogen bonding will increase the bond. So it would dissolve less in water or in other gas. And so its solubility would reduce. So do you understand what I'm trying to say here? Can I get a response? Do you understand now? So looking at the table, you're looking at molecular weight. The larger the molecular weight, the less the surface area, and the higher the lesser the solubility. Am I? Sorry, I've mixed it up. Look at this table again. Sorry, look at the table. Sorry, everybody, look at the table. Look at the molecular weight. The molecular weight is increasing down this way, and the solubility is increasing. The solubility is increasing. Solubility is increasing. The molecular weight is increasing. As the molecular weight increases, solubility is increasing. The solubility is increasing. So that's what's happening here. The solubility is increasing as the molecular weight is increasing. The solubility is increasing as the molecular weight is increasing. But between CO and this, the molecular weight of CO and nitrogen is supposed to increase, so it's increasing. But really, in reality, CO will be less soluble than nitrogen because of the polarity effect. Oh, but I think okay, I've corrected my error. I hope I've not confused you. I repeat, as the molecular weight is increasing, the solubility is increasing. As the molecular weight is increasing, the solubility is increasing. But polarity might have a negative effect on the solubility in certain instances. Polarity. Looking at this, even though CO is slightly heavier than nitrogen, and yes, here it's increasing, but in some instances, the solubility of CO might reduce because of the presence of polarity. There's oxygen. Oxygen would in oxygen and carbon do not have the same polarity. Oxygen is a bit electronegative, so it will pull the electron, bringing in some polarity here, and in some instances might reduce this solubility of CO. But in all instances, the nitrogen gas will always would be like this. So looking at the value, the solubility is increasing. Let's look at polarity. You see the effect of polarity more obvious here as we deal with liquids. The effect of polarity was not so obvious in this gaseous substance, but in some instances you might see it having effect on it. So polarity. Now, if you have, so generally for gases, the one that is more at play, the one that affects it more is the molecular weight. In gases, the molecular weight is more important than polarity. Polarity in some instance might affect it, but the molecular weight is more important in predicting the solubility of the substance. Now, for liquid, now let's look at it. Polar liquids tend to dissolve in polar substance. This is due to dipole interactions. Water is polar and able to form hydrogen bonds with molecules. So we know that in water you have H2O. So because you have H, you have oxygen. Oxygen is electronegative. Oxygen will pull the bonds to itself. Oxygen will pull the bonds to itself, so becoming a bit oxygen will pull the bond to itself, and so the covalent bond will have delta charges, will have slight charges, thus making it polar. And so when it's in contact with other polar molecules, there will be attraction. The oxygen will attract the hydrogen or the positive charge of that polar molecule, thus increasing the solubility. So I repeat myself, polar liquids like oxygen would want to dissolve polar substance. Polar substances more due to dipole interaction and due to hydrogen bonding. So in dipole interaction, looking at it here, you see that the hydrogen goes to one side, the oxygen goes to one side. There's a pull of the bond.
Yes, good morning.
So
You have to get the bonnet right.
You have a positive charge and a negative charge. And this dipole interaction further leads to the hydrogen bonding. If there's hydrogen in the other molecule, the hydrogen will attract the oxygen. The hydrogen of the water molecule will attract the negative charge of the other molecule. Acetone and water will mix in all proportion. Why? Acetone has acetone, if you know the molecular formula of acetone, acetone is CHO. Acetone has a CHO. Acetone has a CHO. It has a single bond bonded to hydrogen. Somebody please mute yourself. Acetone has a hydrogen bond and an oxygen bond, a double bond linking to oxygen. So this leads to a dipole moment there. So oxygen will take the electrons in the bond, leading to a delta negative. Now, if acetone mixes with oxygen, you know that if acetone mixes with water, you know water also has a delta H and a delta negative. So this leads to like hydrogen bonding, and this makes it very soluble in water. But hexane will not mix with water. Hexane has no dipole moments. It has no dipole interaction. In hexane, you have a CH all through, CH bond. So there's nothing withdrawing or pulling the electron. So there's no dipole charge in it. There's no dipole moment in it. So if you mix it with water, there's nothing for water to use to interact with it. So it will be immiscible with water. So when you're dealing with liquids, what you must consider very well is the polarity. But when you're dealing with gaseous substance, what you must consider is the molecular mass, the weight. Polarity plays a role, but very insignificant. But in liquid, polarity is very important. And that's why in the other graph, in the other table, as the molecular weight of the substance increased, the solubility increased because it has a wider surface area. It has a wider surface area to interact with the solvents, and so solubility increased. But for liquids, yes, the molecular weight is very important, but the polarity is more important when you're dealing with liquids. So that table, let me repeat myself. Look at the table. The molecular weight is more important when you're dealing with gaseous substance. So you need more of the molecular weight to predict the solubility of the gas. So here you see that the molecular weight is more important to predict the solubility. As the molecular weight increases, the solubility increases because the surface area is increasing. That's why I use the sugar case to explain. There's polarity occurring in the CO. The polarity is not playing a significant role here. But when you deal with liquids, polarity is very important. do a recap again. I said 3 things affect the solubility of substances. 1, what did I say are the 3 things that affect the solubility? Solute-solvent interaction, temperature effect, and pressure effect. Now we are still under solute-solvent interaction. Under solute-solvent interaction, we have the molecular mass and the polarity. When you are dealing with gases, molecular mass is most significant. Polarity plays a role, but the molecular mass is most significant because as the surface area is increasing, solubility is increasing. Now, when you're dealing with liquids, solubility plays most important, even though molecular weight is important. But the solubility, the polarity plays more significant role in predicting the solubility. So when you're dealing with polar substances will most likely dissolve in polar solvent. And will not a non-polar substance will not dissolve in polar solvent. This is because of the dipole moment that occurs in polar substances. When you talk about polar substances, the oxygen will pull, or the electronegative element will pull the electrons to itself, making a partial dipole moment present, such that you have a negative and a positive charge, even though they are organic substances. And so they will not be able to dissolve in water, which is polar. Water has oxygen and hydrogen, so the oxygen pulls the electron to itself, making it partially polar. And so it's able to become a polar substance that's able to dissolve polar substances. Polarity. So we are still on polarity. Gaseous gasoline mixture of hydrocarbon is a mixable with water, yes, because gasoline is purely non-polar, so it will mix with water. When CC compounds that are rich in carbon are not polar, so most likely will not dissolve in water. Compounds that are rich in CH are nearly non-polar. CH are slightly polar, but the polarity is small. It's small. So most times they would behave as non-polar. CH, carbon is a bit, when you look at on the electronegativity scale, carbon is a bit slight electronegativity compared to hydrogen. Hydrogen is totally electropositive, but it's not significant enough to cause the solution. Non-polar liquids tend to be insoluble in polar liquids. Hexane is totally insoluble in water. The number of carbon atoms in a hydrocarbon affects the solubility of water. The number of hydrocarbon in an atom will affect its solubility in water. I will take it up from here in our next class. So today we introduced the concept of solution. I introduced the concept of mixture. I introduced the concept of saturation and unsaturation and supersaturation. I introduced the concept of solubility. And under solubility, the factors that affect solubility are solvent-solute interaction, a temperature effect, and pressure effect. Under solvent-solute interaction, we have 2 main things: the molecular weight and the polarity. Molecular weight affects more of gaseous substance, while polarity affects more of liquid substance. We call it a day. We'll continue in our next class. By God's grace, please come in promptly so that you get the full everything. I don't know how to link up with you people to give you the slides I want to share with you. If you hold on a little, I'll share the slides in the chat. Can I? And everybody will download it there. So if you hold on a little, I can share this. Yes. Yes. I can't share here. So I don't know how to share. I don't know what to do. Maybe I'll get the coordinator. I guess the coordinator has a way of reaching you. Or maybe I should drop my email here. Or we go to LMS. I'll see if I can drop my stuff. All of you have access to the LMS. I'll drop the slide on LMS. And if I can't, then I'll find a way to drop the slide to you before the next lecture. All right, we're calling it a day. Bye.
Ma, you can send them to the course rep group.
Am I on the course rep group? Somebody, one of you should come, one course rep should come and look for me in Faculty of Science. So when I'm Dr. Fatusi, when you look for me, and then you add me to the course rep group, I'll now drop it there. So the course reps will now send all the slides. So please come and look for me in chemistry. I'm in Science Annex, room 10. Dr. Yola is written on my door because that's not my office, but I stay in her office. So Dr. Yola is written on the door, you will find me, but my name is Dr. Fatusi. Room 10, the bungalow annex. There are 2 annexes in science. My office is in the double-story, 2-story building annex, but the office I stay in is in the bungalow annex, room 10. On the door is written Dr. Oyiyola. Please, some course reps should come and look for me, get my number, add it there, and then I'll drop the slides. Please, I'll be expecting you this week before Wednesday so that I'll get into the slides. Thank you very much.